Assalamu alaikum. So today we are going to do the question paper 9701 Winters 42. Okay. Starting with the question number 3. So in this question they are asking us that we need to write down the standard electrode potential definition. So electrode potential is the potential of any half cell that you get when you compare that half cell with the standard hydrogen electrode. Okay. So you can say that the voltage produced when you're comparing the half cell with the standard hydrogen electrode. Okay, and they have mentioned that you need to include the standard conditions. So standard conditions would be 1 mole per decimeter cube. Okay, and we have 298 Kelvin. Okay, and we have 1 atmospheric pressure. These are the standard conditions. Okay, then we have the next question where they are asking us to complete the electrochemical cell diagram for magnesium and magnetines. Okay, so because both of them, the magnetines and the magnesiines, they are ions, so we can use the half cells like this. Okay, so in this half cell, it's completely up to you whether you want to make Mg the right one or magnet the left one. Okay, that doesn't make any problem here. Okay, so we have first of all making electrode here. Okay, we have voltmeter, and then we have the platinum electrode, because look, whenever we have ions, both of them means the reduced species and the oxidized species, both of them are ions, they must be present in the solution. Okay, and for the reaction to happen in that half cell, we need an electrode that must be made up of some inert metal. Okay, so I'm going to take platinum here. So this one is our platinum. Okay, and we have these Mn2 plus signs here, and we have some MnO4 minus signs. Okay, they are aqueous, so you can write aqueous here. Okay, and on this side we have magnesium, because magnesium exists as a solid metal now, so its electrode will be there in the left hand side half cell. Okay, and we have Mg2 plus ions here, Mg2 plus. Okay, these things, and one more thing, that we need to get a salt bridge here. Okay, and you need to mention it, salt bridge. Okay. These are the some important things that you can mention in any electrochemical cell diagram. Okay, if they are asking us to mention the standard conditions, you can mention them here. That is again 1 atmospheric pressure, we have 298 Kelvin, and 1 mole per decimeter cube solution. Okay, that's all. And then we have the next question. Yeah, we need to make the signs positive and negative on the electrodes, and also need to show the direction of electrons. So let's get back the diagram again. I think I can get it here. Okay, so the positive electrode will be our cathode in this electrochemical cell. Okay, and the negative one will be our anode. Okay, so according to the values that they have given us in this table. Okay, now look, we have this thing, magnesium is minus value, means its electrode potential is in negatives, and we have magnesiines. Look, they were asking for MnO4 minus and Mn2 plus. Okay, we only have this equation that represents the same ions in the both in one equation. Okay, so 1.52, and we already know that whenever we have electrode potential value in positives, or we can say that more positive the value, the equation will be reduced, or the reactant will be reduced. Okay, means a reduction will happen on this side, and the smaller the electrode potential values, the oxidation will happen in that half cell. Okay, so it means according to the diagram that I have made, this, the half cell where this reaction is happening, it will be considered as a cathode. Okay, because reduction always happen at the cathode, and this one will be considered as anode. Okay, and so according to my picture that I had drawn earlier, it was that this one was magnesium half cell. Okay, and this one was MnO4 half cell, so it will contain the, because it is cathode now, so it will contain the positive sign and it will contain the negative sign. Okay, and electrons always flow from negative to positive, okay, from anode to cathode. So it means, according to my diagram, the electron movement will be from left to right side. Okay, you can draw it like this. Is that clear? Now the next question that we have here is the cell potential. So the cell potential formula is simple. We have E cell, okay, that is reduction half cell electrode potential value minus the oxidation half cell electrode potential value. Okay, so this one we have reduction was, I think it was 1.5. Let me check. Yeah, 1.52 and 2.38. So we have 1.58, sorry, it was 1.52 minus, then minus 2.38. Okay, and then our answer should be, wait, let me just calculate it. I don't have the calculator right now. Okay, so we have 1.52 and 2.38. We need to add them because the signs will be positive. So it's 3.90. So we have 3.90 as our final value for the overall cell potential. Okay, now the next question is that we need to write the overall equation for the cell reaction. Okay, that's an interesting thing here. Okay, we need to pick our equations. This one is our reduction equation and this one is our oxidation equation. Okay, keep that one point in your mind, that whenever you are going to write the overall equation, you always have to reverse the equation whose electrode potential is smaller. Okay, so it means that I'm going to reverse this equation. It will become Mg losing 2 electrons and forming Mg2 plus 2 electrons. Okay, this is the equation that I'm going to use, and this equation will remain same because it's the reduction equation. The next thing is that you always have to balance out your electrons. In both equations, there should be equal electrons. So we have 5 here, but in this equation, we have only 2 electrons. It means that we can multiply the above equation with 5, the whole equation with 5. Okay, and we can multiply the reduction equation with 2. Okay, so after multiplying, we are going to get these two equations. Let me write them here. It will be 2, 8 will become 16, 5 will become 10, and it will again 2 and it will become 8. Okay, and this one, the original equation was Mg, it 5, giving us 5 Mg2 plus we have 10 electrons. Okay, this is the oxidation equation, this is the reduction equation. Now the only thing that you need to do, just cancel out the similar terms and write your overall equation. So it should be 10 electrons will be cancelled by these 10 electrons, these one. Okay, so we are just left with 5 Mg plus 2 MnO4 negative plus 16 H positives, okay, giving us 5 Mg2 plus, and we have 2 Mn2 plus I'm going to write the water here, it's 8 water. Okay, so this is your final equation that you can write in the questions place. Okay, so this one. And now the next question. Predict how the cell reaction will change, if at all, when the solution in Mg2 plus is diluted by the addition of a large volume of water. Explain your answer. Okay, so what happens that they are asking us that we need to dilute the solution, right, in the half cell when we are adding Mg2 plus. Okay, so our equation for the overall reaction, there will be no change. Okay, because the dilution doesn't change the equation. The Mg is still losing the electrons and magnetite still gaining the electrons. Okay, but yes, there will be some effect on the value of electrode potential of magnesium half cell. Okay, the left one that I have drawn. Okay, so in this one, because we are making Mg2 plus more, the overall half cell more diluted, so it means you can say that Mg, wait, I'm going to write the original equation, of course, Mg2 plus gaining 2 electrons and making Mg here. If you are making the solution more diluted, it means Mg2 plus concentration will become smaller, or it will become less in the half cell. Okay, and whenever the reactant site concentration become less, the backward reaction will be favorable. Okay, and or you can say the equilibrium will shift towards the left side, and when it is becoming towards the left side, so our equation, you can say that electrode potential will become more negative. Okay, that's always the case, that whenever the backward reaction is favorable, the electrode potential always decreases. Okay, so because our original value was minus 2.38, so it will become more negative. Okay, it can become 4, it can become 5, but that depend, you can just write more negative. Okay, now the next question, we have a molten magnesium salt is electrolyzed for 15 minutes. Okay, so we have the time here. Time is 15 minutes. It means you always need to convert it into your seconds. Okay, so we have, okay, so the time is 15 minutes. You always need to convert it into seconds. So 15 times 60 will give us the time in the seconds. That should be 15 times 60. It's 900 seconds. Okay, okay, and at the electrode, at cathode, they have given us the magnesium atoms. Okay, you always need to get number of moles for your calculation. Okay, so we are going to use the formula number of particles is equal to moles times Avogadro's constant. Okay, you must have done this formula in your IGs or in your AS level. Okay, so to get the number of moles, we are going to change the positions of the variables here. So it will become moles is equal to number of particles or number of atoms, because in this case we have atoms here of magnesium. Okay, and divided by Avogadro's constant. So it's 4.75 10 raised to power 22. We have, and Avogadro's is 6.02 10 raised to power 23. And if you divide them, what answer? We just wait a second. It must be 0.78. Just give me 1 minute. My calculator is having some problems here. Okay, so the answer for number of moles is 0.078. Okay, these are the moles here. Then, okay, the next step is always you need to find out your equation or the reaction that is happening at cathode. So magnesium atoms are, or magnesium metal is produced at cathode. So Mg from the solution is gaining 2 electrons to make Mg. Okay, and 2 moles of electrons means overall 2 Faradays. So we're writing 2 Faraday. 2 Faraday charge is making 1 mole of magnesium. Okay, and we need to find out that how many coulombs of the how many coulombs of electricity will be able to make 0.078 moles. Okay, it means that you can just simply have to cross multiply, but of course, wait, let me just rearrange this formula. It can be 0.078 mole is equal to Q divided by 2F and times 1 mole. Okay, it's not something complicated. I've just rearranged the previous thing here. Okay, so we need to find out Q here. Rearranging this, we have 0.078 times 2, and for Faraday's value we have 96,500. Okay, divided by 1 mole, and we have Q here. Okay, and the overall value that we are getting for this Q is 15,054 coulombs. Okay, and to find out the current, the equation is Q is equal to IT. So Q divided by T will give us I. Current is sorry, the charge is 15,054. The time that we have already measured, that was 900 seconds. So the answer will be that I have got it 16.72. Okay, so that's our answer, and this is how you can calculate these type of questions. Okay, so that was all for the question number 3. Allah Hafiz.